I'm Madene, and today I would like to share my experiences and the lessons that I learned while developing a next generation web application. I am a software engineer at Intellect, and as part of my day-to-day work there, I mostly develop web apps. And I particularly enjoy the front-end side of things, since I see myself as a bit of an artist, because I can use code to create a product for a client that not only satisfies the business requirements, but that looks great and that users will actually enjoy. At Intellect, we work hard, but we also like having fun. And since I'm part of Intellect's social committee, I help to organize social events and initiatives for the employees. In my free time, I really enjoy mountain biking, and I also really like traveling. I'm a bit of a foodie as well, so I really enjoy good food. And I must admit, I am a movie snob, so I enjoy all the artsy, Oscar-nominated films. So, okay, enough about me. I'd like to tell you a bit more about the project that I've been working on for almost a year and a half now. And my whole talk is based on my experiences and the lessons that I learned while working on this project. So our client is a chemicals company, and they have an agricultural division. And this division produces fertilizer on a very large scale, and they sell this fertilizer to some of the most prestigious farmers in the country. And before starting with this project, I was actually unaware of the precise science behind farming practices. So it's actually a very interesting and unusual domain for a developer to work in. So they have sales representatives that travel far and wide over the country in their Hilux bakkies to the farmers, and those farmers are usually in areas with low network coverage. So our client needed an app that the sales reps could use to create orders for fertilizer while they're at the customer, which could be in areas with no network coverage. And what's more, the sales reps would be using their own devices to create orders and use the app. So this could be a mobile device, a tablet, or a laptop. And the client also wanted the same app to be available for the back office personnel, who would be using the app on desktops. So the solution that we came up with was an application that's reliable in environments with poor network coverage and that can be used on any device. So basically what we were striving for was an innovative new way to create applications for mobile devices. Apps that look and behave exactly like apps on a phone. Just put them on an internet server. They're also easy to update. So you'd think that someone said this last year, but in actual fact, it was Steve Jobs that said this at the launch of the iPhone in 2007. This was how he described to develop apps for the very first iPhone, and it was surprisingly web apps. Little did he know that almost 10 years later, Google would coin this term as progressive web apps. A progressive web app is a website built using modern web technologies, but acts and feels like a mobile app. Progressive web apps are useful from the very first time you visit them in a browser. No installation required. Then, as you progressively build a relationship with the app over time, it becomes more and more powerful. It progressively starts unveiling more and more features as your browser's technology improves, independent of the operating system. Progressive web apps have various characteristics that make them behave and act like mobile apps. They are reliable in offline environments, so they load instantly even in uncertain network conditions. They are fast, so they respond quickly to user interactions and they have silky smooth animations. They make re-engagement with their users possible through features like push notifications. They're even installable to your home screen, and when you launch them from there, they load as a full screen app-like experience. They're also responsive since they need to fit any screen size from a mobile device to a desktop. And since they are required to be served over HTTPS, it also means that they are safe and secure. So a lot of these characteristics made progressive web apps a perfect fit for our project. Since you only need a browser to access the app, it would be available across multiple platforms and on various devices, independent of the operating system. Our team was also already very familiar with web technology, and therefore we could utilize our existing knowledge of web development to build the app. Since you only need one skill set to work on the app, it also makes training and hiring people much easier as well, since you don't need knowledge of all the various languages of all the native platforms. Since we were only building one web app, we'd have a single code base, which lowers the development and maintenance costs. I'm sure some of you are familiar with multiple code bases, and you'd know that they are plagued with inconsistencies since multiple teams work on them. So a single code base also gives you much more consistency. Our app would also be used for many years to come, and therefore you also had to cater for the possibility of future platforms. So, for example, if the Chrome operating system becomes mainstream, we'd already have support for that. And then, lastly, browsers are constantly optimizing their code for older devices, and that meant the features of our app could adapt to work reliably and fast even on older devices. So the biggest hurdle or challenge for us in our project was the offline capabilities. Offline capabilities aren't normally associated with web apps, but the latest advancements in web technology have actually made it possible to develop a web app that can function regardless of the network state. So let's have a look at how we developed a truly offline-first web app. In order for your app to work offline, you obviously have to store some data on the user's device. There are two types of data that you need to consider: static content and dynamic content. So static content are network resources that are necessary for your app to load in offline environments. So for example, your app's shell. This could include HTML, CSS, JavaScript, all the resources that you need to load your app while offline. Then you also have dynamic content. Dynamic content changes based on your user's preferences, and it causes changes to your website. So for example, this could be a list of news articles specific for a user. The biggest enabler for storing static content is the service worker. So a service worker is a script that your browser runs in the background, separate from your web page. It has the ability to intercept network requests and respond to them in various ways. It also provides you with 3 APIs that give your app some mobile-like functionality. So the first one is push notifications. By using the push API, you can send updates to your user, for example, a breaking news article. Then, since you can intercept all network requests, it gives you very fine-grained control over the caching of your app. It even allows you to pre-cache some resources even before the user has accessed them. There are various caching mechanisms or strategies that your service worker can use, and I'm going to explain one of them in a few moments. Then we also have the background sync API. This allows you to send messages to the server even when the app isn't open in the browser. Cool, so let's have a look at one of the caching strategies that the service worker can use. This strategy is called cache and update, and it involves serving content from the cache while updating the cache with the latest resource from the network. So the process starts off with your app requesting a resource from the network. The service worker then intercepts this request and it forwards that request to the network. If the server is taking a bit too long to respond, so let's say 400 milliseconds, the service worker then goes and has a look in the cache to see if it has a local copy of that same resource. If it finds a cached version, it then responds to the original request with that local copy. In the meantime, the response may come back from the server. The service worker once again intercepts that response, and then it updates the cache with the latest version of the resource from the network. So with this strategy on a fast network, the user will have the best experience, since the user will always have access to the latest version of the app. However, if for example, it's the sales rep that's on a farm, he at least wants to be able to create his order, so then it's okay if he's using an older version of the app, because at least he can still get some work done, and then eventually he will get the latest version of the app. On our journey with service workers, we did encounter a few unexpected hurdles, and I would just like to give you a heads up on that. So we used Angular for our front end, and we made use of a library called Workbox to generate our service worker. And Workbox makes it really easy for you to pre-cache your resources by generating a revision number per file. And this revision number is based on the contents of the file. So whenever the contents change, the revision number is updated, and the service worker knows to go and fetch that there's a new version on the server available. However, if you are making changes to your files after building your app, for example, string replacing some variables based on the environment, that revision number is not going to update because the revision number was created before building the app. Therefore, the service worker isn't going to know that there's a new version available on the server. So, how we worked around that issue was we have a version variable that we always replace before building our app. And that way we can ensure that the config file always has a new revision number, and the service worker will always fetch the new config from the server. Okay, something else to remember with service workers. Service workers don't only cache the response's body, they cache the headers as well. So if you are setting some headers on your API, for example, content security policies, the revision number of that file is not going to update unless the contents of the file updated. So if you make changes on your API to the headers, but your service worker isn't fetching any new resources, you'll be stuck with those old headers in the browser. Then lastly, the new version of your app is not going to be available until you explicitly activate your new service worker. So you can do this by listening for a specific event in the life cycle of the service worker and display a banner in your app, for example, that asks the user, would he like to update the app now or later? Otherwise, if you don't do this, your user will be stuck with an old version of your app, and it won't update. So the service worker makes use of the cache API to store all your static content. But for dynamic content, it's better to use IndexedDB. So IndexedDB is a low-level API for client-side storage. And you can actually store large amounts of data in IndexedDB, including files or blobs. IndexedDB is asynchronous, meaning you can execute queries on IndexedDB without blocking your application. The indexes enable you to perform high-performance searches on large amounts of data. And IndexedDB is also transactional, meaning that it retrieves and updates data in a series of transactions. So a lot of these traits made IndexedDB an ideal fit for our project. Since we'd be storing all the dynamic data locally on the device, our app would always have access to that data, no matter the network conditions. Because of the user's domain and the amount of data that we'd be storing, the indexes ensured we could perform quick searches, and our users received quick feedback, and the app remained responsive. We were also integrating with an external system for all of our data, and we were receiving that data from them in a structured format. And since IndexedDB works with key value pairs, we could just store the data as is. We didn't need to go and translate those documents into a relational model. There is one catch with IndexedDB, however, and that is the limit on the amount of data you can store. So the amount of data you can store depends on the browser. So in Chrome, for example, you can use up to 6% of the free disk space. So on a desktop, this may sound like a lot, but when it comes to a mobile device, it's not that much anymore. So that's why you need to keep these numbers in mind. In Firefox, you can store up to 10% of free disk space. Safari for iOS maxes out at 50 megabytes, whereas Safari for Mac, you have unlimited storage. In Internet Explorer 10, the maximum is 250 megabytes, where on Edge, it depends on the volume size. So the larger the volume, the more you can store. When the browser is under storage pressure, so when space is becoming limited, it will actually automatically clear the data that has been stored. And for an offline app, that could be a disaster because the user expects the app to work offline. So what you could do is you could make use of the persistence API. So with the persistence API, you can request permission from the browser to persist the user's data. Under certain conditions, the browser will grant that permission, and then it will actually not automatically clear the user's data. It will prompt the user to go and manually clear the data. So that just gives the user much more control over what is actually cleared, and it provides a much more reliable experience. So now that we have the storage limitations covered, how did we actually keep all this dynamic data up to date? Well, the answer is actually quite simple. WebSockets. By using WebSockets, we were able to achieve an offline sync that was quick and that used the minimum amount of data. Since the WebSocket is always connected while the user is browsing the app, we could quickly send and receive messages that were, data that was available both on the client and on the server. We also used a push-based mechanism where the server pushes any new changes to the browser. So that meant we only ever sent data that actually changed, and the client didn't have to constantly poll for the latest changes. We also have real-time interaction between a user's browsers. For example, if the sales rep created the order on his phone, within moments he could see that same order on his laptop. There is one drawback with this mechanism, and that is that data can only be synced while the app is actually open in the browser. So in the future, we'll also have to cater for scenarios where data can get synced while the website isn't even open in the browser. So there are two ways how you can achieve a background sync. The first mechanism involves the service worker. So you use the background sync API inside the service worker. So for example, if the sales rep was on a farm at the customer, there was no network coverage, he creates an order and he closes the app in the browser, gets into his bakkie, drives home, and then on his way home, he regains connectivity. Chrome's process then wakes up your app service worker. And the service worker then sends all those pending updates that were made while the device was offline to the server. The background sync API is only supported in Chrome at the moment, unfortunately. So for other browsers, you can also use push notifications to achieve a similar effect. So with this mechanism, the server can periodically send push notifications to the app, say every hour, and this will then initiate a sync where the service worker sends all the pending updates to the server, and the server can then actually respond with all the latest changes that were made on other devices. So by using one of these two mechanisms, you can be assured that all the latest changes are on your API, and your user has access to the latest data when he or she opens the app. So now we have all of the data stored locally on the device. Only problem is, sorry, can we, can, yes, you will have to implement collision detection and conflict management on your API. Yes. Yes. Sorry, can we keep all questions till the end, please? Thanks. Cool. So now we have all the data stored on the user's device. Only problem is there was a lot of it, which led us to our next concern, performance. We needed to come up with all kinds of creative ways to ensure that the app performed at its most optimal, regardless of the amount of data that was stored, the network state, and which device it was running on. So if you recall, I mentioned earlier that IndexedDB is asynchronous and that it doesn't block your application. Well, this is only partially true, and as we all know, browsers just love adhering to web standards. Surprisingly, it was actually Chrome that degraded the performance of your app while executing queries on IndexedDB on large amounts of data. We found that Chrome actually blocks the main user interface thread while executing these queries. Luckily, Werkers came to our rescue. So Werkers is a way for you to run scripts in the background, separate from other scripts. So what we decided to do is to move all of our database queries into a web worker. And since these queries would be executed on a background thread, Chrome could do all the blocking it wanted to, but our app remained responsive. Werkers also have this cool sharing feature where you can unify work and sync data across multiple browser tabs. And what's also really nice about Werkers is they are supported in all the major browsers. However, shared Werkers are only supported in a few. So Werkers communicate with the main script via messages. And since those messages are deserialized on the main user interface thread, it's advisable to keep those messages as small as possible. So that's why we decided to post each entry that we retrieved from the database separately on a message. However, we were using Angular, and Angular has this feature called zones. So for those of you who aren't familiar with Angular, it is a JavaScript framework that helps developers to build web apps. So it's just a bunch of libraries that make it easier for you to implement some of the more complicated requirements for web apps. Right, so Angular has this concept of a zone, which acts as a boundary between changes happening inside Angular and changes happening in the outside world. So for example, network requests, user clicks, and in our case, messages from the web worker. So Angular constantly monitors this boundary, and whenever an external event crosses that boundary, Angular re-evaluates all the bounded variables in order to determine what it should update on the user interface. So for a developer, this is amazing because you can fire off network requests, and when the response comes back, the user interface just magically updates. However, in our case, it was causing chaos. So imagine retrieving 2,000 products from IndexedDB. This change detection cycle would then run for each entry retrieved. In other words, 2,000 times. And this caused our app to slow down a lot. So to counteract this effect, we decided to process all our data results outside of the Angular zone. And then once we retrieved all of the results, we manually triggered Angular's change detection and zone to run, which drastically improved the performance of our app. So now we had the Angular zone issue sorted, but now we had to display 2,000 items on the front end. And rendering 2,000 elements in the DOM isn't really advisable. That's why we used virtual scrolling. So virtual scrolling allows you to display an infinitely growing list in a very efficient way. So how it works is it only displays the amount of elements that are actually visible inside the viewport. And then as the user scrolls, it reuses those elements. So what makes it efficient is you are only displaying a small constant amount of elements at a time, regardless of the size of the list. So just to give you an example, at the beginning stages of the project, the API that we were integrating with didn't have any user filtering. So we were receiving 14,000 customers from their API. We were storing this in IndexedDB and displaying it using virtual scroll, and our app didn't show any degradation in performance, which I think is an amazing testimony as to the amount of data that you can actually store in IndexedDB and can display using virtual scroll. Right, so now we have all the bits and pieces, but how do they all fit together? So let's have a look at how all the components work together in our architecture. Cool, so we were storing dynamic data in IndexedDB on the user's device, and we needed to execute some queries on IndexedDB. We were performing create, update, and delete queries. We weren't performing a lot of them, so we could execute them directly from the Angular app. However, we were reading large amounts of data. Then we found the blocking issue on Chrome, so we decided to move all of our queries to the web worker. And we had the issue with Angular Zone, so we processed all of that data outside of the Angular Zone, and then once we had all the results, manually triggered Angular Zone to run. We also needed to store static resources. We needed to store our app shell so that it could load in offline environments. For that, we used the service worker. So the service worker intercepts all GET requests, and then it either serves the latest version from the network or a local copy from the cache. We needed to keep all our dynamic resources in sync. And for this, we also used a web worker. So the web worker established a WebSocket connection with the server, and then it retrieves all the changes that the app didn't have yet. As I said, we were also performing some updates inside the app, for example, creating an orders. And in those cases, the Angular app would notify the sync web worker of the change. The web worker then retrieves that change from IndexedDB, and it sends that change to the server via the WebSocket connection. Let's just do a quick recap of all the tech we've covered as well. So a service worker is a script that your browser runs in the background, and it enhances your app with some offline capabilities and also some app-like behavior. A web worker is also a script that your browser runs in the background, but it allows you to do some work without affecting your user interface. So it can help you to improve the performance of your app. Then we also had a look at IndexedDB. So IndexedDB is a structured storage that allows you to store dynamic data, and it provides your user with a reliable and a fast experience. So when building a web app, it's always important to keep browser support in mind, and especially with progressive web apps, because they need to work for every user regardless of which browser they are using. So, service workers. Service workers are supported in Chrome, Firefox, Edge, and last year Safari also added support for service workers. An important thing to note about service workers on iOS, they have very limited support, and with very limited, I mean they only work in Safari for iOS. Chrome or any other browser, they don't support service workers, only Safari for iOS. Background sync API is unfortunately only supported in Chrome, and for the other browsers, you'll have to maybe use push notifications to achieve a similar mechanism. So, looking at push notifications, they are supported in Chrome, Firefox, and Edge. Safari for Mac has push notifications, but it doesn't make use of the push API. They have their own implementation. So you'd have to do a custom implementation for Safari for Mac. Safari for iOS, unfortunately, doesn't have support for any push notifications. The second version of IndexedDB is supported in Chrome, Firefox, and Safari. Edge does have support for the first version of IndexedDB. And web workers are supported in all of the major browsers. Shared web workers that can be shared across multiple browser tabs are only supported in Chrome and Firefox. So when supporting multiple browsers, there are a few things that you need to keep in mind. So in some cases where there is a feature that you want to use and it's not available in the browser, you can use a polyfill. So a polyfill is a browser fallback. So it's basically just a JavaScript library that provides functionality that you as a developer expect the browser to provide natively. So for example, IndexedDB actually has a polyfill. Then the background sync. As I said, it's very limited support, the sync API is only supported in Chrome, and therefore you'll have to come up with some creative ways to achieve a similar effect in other browsers. Then lastly, if the browser doesn't support a feature, it shouldn't prevent your user from using your app. The app shouldn't break. And that's why you need graceful fallbacks. So for example, you can have a feature toggle that disables a certain feature if you detect that the browser doesn't support some functionality that you need. Right, so that was the current state of technology on the web. Let's have a look at what is on the horizon. So people have become used to looking for apps in app stores. And that's why some of the big companies like Google and Microsoft have actually started adding support for progressive web apps in their app store. So for example, Google, with their release of Chrome 72 for Android at the beginning of the year, they added a feature called Trusted Web Activities. And this will allow you to distribute your PWA in the Google Play Store, which is really cool. Apple, on the other hand, hasn't made any comments about adding support for PWAs in their App Store. However, they have shown support for PWAs through the introduction of Service Workers and the Add to Home Screen functionality. Microsoft will allow manual submissions of PWAs to their App Store, and Bing actually automatically adds PWAs to their App Store if they actually meet certain criteria. Then you can also use a tool. There are certain tools available like PWA Builder that you can use to wrap and package your PWA as a native mobile app, and then you can publish that to the App Store. So with all of these major players pledging support for PWAs, they will continue to improve their browsers as well to provide a better experience for everyone. So one of the new and exciting APIs to look out for in the future is the Web Authentication API. That API will allow you to allow passwordless authentication and two-factor authentication without using SMSs. So imagine logging in on a web page with your fingerprint. This will make authentication on the web much easier, and it can actually standardize authentication on the web. Another cool API is the Streams API. So normally you'll have to wait for the termination signal from the server in order to gain access to a response body. But with the Streams API, you can access the data as it is coming in from the server and update your user interface accordingly. WebAssembly is a new kind of programming language that will allow you to run languages like C++ in the browser. And it's actually designed to work alongside JavaScript, so the two play very well together. And maybe what we could be seeing in the future is frameworks like Angular using WebAssembly to improve the performance of their framework and apps built on it. Web share, payment requests, shape detection, those are all new APIs that may be added in the future and that you can look out for. So as progressive web apps grow in popularity, they will get more and more access to the native APIs that were previously only reserved for native mobile apps. An example of one of the APIs is device orientation. So this will allow you to gain access to the physical orientation of the device. So imagine having the Sky Maps app that is used, you can use that to point to the sky and see the star constellations. Imagine building an app like that, but for the web. Then media capturing will grant you access to the device's camera, and then you can use that for image capturing, for example, scanning a QR code. Then vibration, that can allow you to give non-audible feedback to your user. So for example, if a breaking news story comes through, you can add a vibration to that alert. Then a really cool one is the ambient light API. That gives you access to the light intensity level that is measured by the device's light sensor. So that could, for example, allow you to switch your app between light and dark theme, depending on the light in the surroundings. So with all of these new and exciting advancements in web technology, I'd like to leave you with the following inspiration to always look for new and better ways to do things. The key is to embrace disruption and change early. Don't react to it decades later. You can't fight innovation. As part of our engagement with our clients, we have developed many native apps for them in the past. And for this solution, we could have gone the normal route, but we decided to try out progressive web apps instead. And it turned out to be a decision that not only benefited us, but also that will benefit the client in the years to come. Thank you very much. Thanks for listening.